Welcome to The Explainer. Today, we're diving into a breakthrough that could completely reshape our technology. And believe it or not, it all starts with a metal you know really well, gold. But forget what you know about jewelry. We're talking about unlocking its secret quantum power. Okay, so we're always hearing about the incredible promise of quantum computing, right? How it's going to solve these impossible problems, create new medicines, the whole shebang. So, why isn't there a powerful quantum computer sitting on your desk right now? What's the big holdup? Well, it really boils down to something researchers call the quantum scaling problem. And at its core, it's a huge conflict in the way we're trying to build these things. See, on one hand, you've got these systems like trapped ions. Quantum-wise, they're perfect. You can control them with amazing precision. But, and it's a big but, they are incredibly fragile and just unbelievably hard to link together. Imagine trying to build a skyscraper out of delicate, floating soap bubbles. It's kind of like that. For a quantum computer to actually be useful, we need millions of these quantum bits or qubits all working together on a stable, solid platform. And that's the real challenge. So, how in the world do you solve a problem like that? Well, the solution comes from a place you would never expect. Scientists didn't just find some new material, they actually created one by playing with gold at the atomic level. What they came up with are these gold superatomic clusters. Now, this concept is just wild. This isn't just a tiny flake of gold. It's a particle that's built with a very specific number of gold atoms, and it acts like one single giant artificial atom. So you get the amazing quantum properties of a single fragile atom, but with the sturdiness of a solid material. It's literally the best of both worlds. And here it is, the star of the show, the Au-25 cluster. That means it has a core of exactly 25 gold atoms, all arranged in a perfect structure. And that number, 25, that's the key. In chemistry, it turns out some numbers are just magic, and 25 creates this incredibly stable electronic shell, something you just don't get with a single gold atom or a random chunk of it. Okay, so we've got our super stable artificial atom. That's great. But for it to be a useful qubit for a computer, you have to be able to do two things: control its state and then read what that state is. And this is where the real magic happens. The secret is in something called spin polarized emission. Now, here's the basic idea. Every electron has a property called spin. You can just think of it as pointing either up or down. What's so cool about these gold clusters is that you can get them to spit out light, where the little particles of light, the photons, carry that spin information with them. It really is like a tiny, controllable spinning quantum flashlight that tells you exactly what's happening inside. And the process for using it is actually pretty elegant. Step 1. You zap the cluster with a laser pulse to give it some energy. Step 2. As that artificial atom relaxes, it shoots out a photon of light that's carrying that critical spin information. And finally, step 3, you just measure the spin of that light. That measurement tells you, directly, the quantum state of the cluster. It's a really clean way to write and read quantum data. And hey, this isn't just a cool theory. They actually proved it works using a super specialized technique. Get ready for it? Called magnetic circularly polarized luminescence spectroscopy, or MCPL, researchers showed they could do it. This fancy setup let them clearly see and tell the difference between the different spin states of the light coming off the cluster. It was the confirmation they needed. They could reliably read the quantum info. So just how good is this quantum flashlight? Well, they measured a spin polarization rate of 40%. Now, to put that into perspective for you, in the quantum world, where information is ridiculously fragile, getting a clear signal that strong is a huge deal. That's a super efficient transfer of information, and it makes these gold superatoms a real contender against other top quantum systems out there. All right, so we've got a stable system that we can control and read. What does a future forged in these tiny gold clusters actually look like? Why does any of this matter? The potential impact here is just massive. And it goes way beyond just making faster computers. I mean, the same thing that lets us read the cluster's state makes them perfect for building ultra-sensitive magnetic sensors. Their unique chemical makeup could make them amazing catalysts for green energy or for discovering new drugs. And this whole thing is fueling a brand new field called spintronics, which uses an electron's spin, not just its charge, to process information. So here's the roadmap. The big breakthrough was back in 2023, when they first showed the stable spin control. The challenge right now is to make that quantum state last longer, what they call coherence time, and, of course, to figure out how to make tons of these things. But the vision? By 2030, the hope is that these gold clusters will be a core ingredient in a whole new generation of quantum tech.
So really, the final takeaway is this. By taking a metal that we've valued for thousands of years and completely re-engineering it atom by atom, scientists have basically created a brand new building block for our technological future. Which leaves us with a pretty mind-blowing question. Could a tiny, perfectly arranged cluster of just 25 atoms of gold be the very key that redefines our entire digital world?